In this lesson, we're going to introduce the concept of a limit, which is a central idea to the study of calculus. Now, in order to actually define limits, we're going to need to talk about them in the context of a function. So let me draw on a function first. Now, in order to actually find a limit on a graph like this, we need to choose an x value that we'd like to approach. And now we can go ahead and just introduce the definition to you. A limit is just the value you seem to approach as you move across the graph from either the right or the left. Now, the reason we actually look at the graph on the right and the left is because the graph might do something really unexpected at this point. So even if the function decided to just randomly jump up like this, the limit actually wouldn't change, because as we come in from the left or from the right, it seems as though we're approaching the same point. Now, just to be totally clear, this y value over here is the limit that we seem to be approaching when we get closer to a. On the other hand, this value over here is the true y value we get when we substitute x equals a into f of x. So you just have to realize that f of a doesn't have to be equal to L, although for most functions in most places it usually would be. For example, if you chose a to be over here, the limit would be the same thing as f of a. Now usually in my head, when I picture limits, I kind of imagine this to be almost like a mountainside, and there are two skiers on either side of the slope. Now if this skier is moving to the right and this skier is moving to the left, then you can think of the limit as the point where their skis will collide. Now let's suppose for a minute that we actually change the graph so that they don't collide. Then in this case we just say that the limit doesn't exist and we leave it at that. Now let's imagine for a moment that the position of this right skier is just x. Then of course the position of the skier is just x f of x. So we can just say that this limit L is just what this skier would approach as their x position gets closer to a. And this is actually reflected in the notation. We see that as x approaches a, f of x eventually becomes L in the limit. The cool thing about a limit is that it doesn't need to know what the value is exactly when x equals a. We just need to know what the nearby values are, and that's more than enough to define the limit. Now initially, this might sound like a bit of a useless thing to do, like why not just sub in the value at a? And the reason is because sometimes the value at a is just not defined. To make this a little bit clearer, let me actually give you an example to show you what I'm talking about. So here it looks like we have a reasonably straightforward looking problem. We're asking what f of x seems to approach as x gets closer and closer to 4. Well, we could just sub in 4, right? That would just tell us what value we're approaching. But something goes a little bit wrong. So we can go ahead and just replace every x for a 4. And now if we just look at the bottom, we notice something a little bit bad's happened. 4 minus 4 is just the same thing as 0. Now as we know, dividing by 0 just makes no sense, so that just means that there's no answer, right? Well, not quite. How about instead we try some values close to 4 to see what happens? Now to actually try some values that are close to 4, I'm going to go ahead and use a spreadsheet. Now to begin with, let me label this column x and this column over here f of x. Now I'd also like to draw out a number line over here so that we can track roughly what's going on. Now we're going to want to pick a whole bunch of x values that we'd like to try, where each one gets a little bit closer to 4. Now I was careful not to actually pick 4 because we know that 4 gives us an error. Now we can go ahead and select this cell and then use this value over here and substitute it into the value of f of x. Now since this cell A2 holds the value of x that we're using, whenever we wanted to type in x, we just use A2. Also, SQRT just means square root. Now the great thing about doing this in a spreadsheet is we can actually copy this and do it for all the other cells very, very quickly. So for example, if you clicked on the cell B4, you'd notice this. Before, we had an A2 in this spot, but now since we're on the 4th row, we now have an A4 instead. Now by looking at the numbers we're getting in our spreadsheet, it looks as though the values are getting very close to 0.25. So we think maybe that's our limit, but we should also check it from the other side as well. Now over here I've written that L minus equals 0.25, because we're coming in from the left. Now again, because we're using a spreadsheet, we can just replace all of these values for values coming in from the other side. So we'll start with 5 and then work our way in towards 4 again. So as you can see, the benefit of using a spreadsheet is that the numbers just magically get updated for you. Now looking at the final number, again it looks like we're getting very, very close to 0.25. And now we don't really need the spreadsheet anymore. Now notice that since the value on the left is 0.25 and the value on the right is 0.25, we're justified in saying that the limit of this function is actually 0.25. And of course 0.25 is the same thing as 1 over 4. Now, if you found yourself in a situation where you didn't have access to a spreadsheet, but you had a calculator handy, you could actually use the calculator to find this limit as well. All you really need to do is to test out a value that's very, very close to 4 in this function. So let me just use 4.001. As you can see, when you substitute a value of 4.001 in, the answer you get is incredibly close to 1 on 4 as well. Now I hope this example has shown you something that you didn't expect. Despite the fact that our function is not defined when x equals 4, the limit is perfectly well defined and it's exactly equal to 1 on 4. So it's exactly like this case we have on the left. The value just gets closer and closer to 1 on 4, but when you finally get there, it just disappears. Now the next thing to say is that finding limits in the most general case can actually be pretty tough sometimes. However, as we saw with our calculator, we can usually approximate limits with our calculators. There are courses in maths that can spend a significant amount of time just teaching you how to find limits. However, your first course in calculus doesn't necessarily need you to be super familiar with how to find really crazy, exotic limits. However, there are some specific cases where the limit just doesn't exist. So there are three main situations where a limit just can't exist. The simplest, as we've already discussed, is when both sides of the limit don't agree with each other. In this case, the limit on the left seems to approach this value, which is L minus, and from the right it seems to approach L plus. You can make this happen really easily if you use a piecewise function like this one. So in this case, if you tried to find the limit as f of x approaches 2, on the left it would just be equal to 2, and on the right it would actually be equal to 4. You can test that if you like. Now it's also possible for the limit not to exist when the values are actually infinite. So as you can see, as x approaches a, the values seem to go all the way up to infinity, and that means the limit is also not defined. This can happen on functions like this one as well. Now if you tried to find the limit as this f of x approached 2, you'll also find that the limit is not defined, because both sides seem to approach infinity. And now there's actually one final situation where limits don't exist, and that's when the values oscillate really rapidly. So as you can see with this function, as we get closer to a, the values start to go up and down really quickly. Now whenever this happens, the limit is also not defined, although admittedly this is a bit of an exotic condition. However, there are some functions that display this behavior. This over here is actually my bad attempt at trying to draw this function over here. If you tried actually subbing in random values, you'd see that they don't seem to approach anything in particular, so the limit is just undefined in this case. So the key takeaway here is that the limit L only exists when x approaches the same value from both sides, and that value has to be finite. Now by now you should have a pretty strong intuitive sense of what limits are and how they're defined. Now despite the fact that your intuition should actually be pretty solid for these things, it isn't usually enough to get away with intuition. Throughout this lesson, I've been saying the word approach a lot, and we should mathematically define what the word approach means if we're actually going to use it to do any calculations. However, as I said earlier, in a first course in calculus, it is more than enough to just be able to sub in nearby points to find out what the limit should be. In fact, it turns out that even the rigorous definition of a limit is just an adaptation of this idea of two skiers skiing into a particular point. So without further ado, I think with this understanding of limits, you should be more than ready to tackle the rest of the subject. So with that, I'd just like to summarize everything. So we said that the limit is the y value that you seem to approach as your x value gets closer and closer to some point a that you're interested in. So our notation tells us that if the limit is L, in the limit as x approaches a, f of x is equal to L. We also said that the value at x equals a is not important. The limit only considers the neighborhood of nearby points, and therefore the value at x equals a doesn't factor into that. On top of this, we said that there are three main ways that your limit can fail to be defined. In the first case where it fails, the limit on the left is equal to this L minus, and the limit on the right is equal to this L plus. If they're not the same, then the limit is not defined, because we require the limit from both sides to be exactly the same for the limit to be defined. In the second case, if the values just seem to shoot off to infinity, then we could say that the limit is infinity, or we could just say that the limit is undefined. And then there is one final case, which admittedly doesn't show up very much, where your function can oscillate really rapidly, and in that case the limit would be undefined at x equals a as well. Now in a future lesson I will cover the more rigorous definition of a limit, And we can use it to do calculations and all of that jazz. But it isn't really important to learn the first time you learn calculus. So at this point, I'd like to say that you've been sufficiently introduced to limits.